Eee, Slaytımızı çalıştıralım. Kalemimi de değiştireyim hemen işaret seçeneklerinden kalemle mavi yapalım. Okay. Eee, Last week we talked about some property. We talked about optimization problems and what are the challenges. And usually, what we were trying to do is either minimizing or maximizing the fitness function, the goodness of the solution, and if you remember, there were some challenges that we can get trapped into local minima, and we should be developing some algorithms. I told you that I will be introducing some algorithms like hill climbing or simulated annealing in order to overcome the trapping that the solution. Uh, Sorry, overcoming the problems such as trapping in a local or local minima or maxima. And I just wanted to remind you that from now on, all the problems we will be dealing will have a fitness function, or we will be trying to solve. I'm sorry, we will try to solve a problem, an engineering problem, or medical problem, management problem, whatever it is. First of all, we have to define a search space, and we have to, by the help of an expert, we will define upper and lower boundaries of the search space in order to narrow down possible cases, etc. And I know that I have already talked about this. I'm just summarizing, and in the meantime, I'm giving you some new concepts which I haven't introduced last week. Uh, if you imagine that this problem is two-dimensional problem, even though FP is shown as a single dimensional, let's say FP and R. Okay, and imagine that this dimension is R, and the other dimension is P, okay? And rather than this fitness value, the FPR value is, as you know, just is valid for only one R value. Imagine that this is a surface, okay? This is a surface like something like this. Or maybe I should be talking about in here. Okay, let's imagine that this is our second dimension, not imagine, it's already been shown here. This problem is two-dimensional, and each dimension has a name, and these values, the colored ones, are the fitness function, fitness values. So if I say F is the fitness, uh, how many parameters it has? It has two parameters, x1 and x2. X1 and x2 is not a point, but the name of the dimensions. If it will be easier for you, let's say this is y and that parameter x. Therefore, this will be x and the other one will be y. Okay, so it will be easier for you to track down. Anyway, uh, if I want to find the minimum point of this function, fxy is it has got some formula, which I'm not capable of giving it right away. And we would like to find out the minimum point. Imagine that we have got a black box, and inside fxy, inside there is a code, but I don't know what's the inside. There is a code capable of calculating that function, and what I should do, I should be feeding x and y value, and it will be spitting out an fitness value. Okay, the inputs will be x and y. Okay, it will be taking two parameters and calculating the fitness function, whatever it is there, and it is spitting out an output, f. The simple and what you are asked for in a given upper and lower boundary, you are asked to find out where the minimum xy pair is, where the fitness function gets minimum. And in order to find out this, we have to find out x and y value where the f function is minimized. Okay, the simplest. By the way, let's write down here lower boundary and upper boundary of, that is upper boundary and that is lower boundary of x, and upper boundary and lower boundary of y. Okay, and let's say at the beginning, the upper boundary for x is 10 and lower boundary is 0, since it is 0. Upper boundary of y is 10 and lower boundary is 0. This they can be different, you know. Sometimes, I mean, not sometimes, depending on the problem, maybe upper boundary and lower boundary of y is somewhere else, -10 and +10, etc. Anyway, the simplest, without any how can I say, if you don't know anything about artificial intelligence, if I ask you to find out where this function is minimized, what you will do, you will randomly produce some coordinates and feed it into this box and get the f value. Whichever is the minimum, you will say that, okay, that is where this function is minimum. Of course, no one will be sure that whether there is another point which has lower value than what you have provided to them, because usually we don't know the fitness function and we don't know the mathematical formulation of this value, so we cannot get the derivative, and we don't know where the exact minimum point is. Usually, the usual cases are the number of parameters are more than 20 or 10 or 30, so that will be really difficult for us to calculate where the function is minimum, because the usual case, this f function is not the derivative of the f function is not possible to calculate most of the times. Anyway, because it is not continuous or blah blah blah blah. So the most naive, the most simple way to solve this problem is, as I told you, throw a random number for x and y within the upper boundary and lower boundaries. That means you randomly created a point and check what the f function is. Okay, by taking the random samples, you may come across, maybe you come across to that point. Okay, and after taking so many samples, you say that you find out this function is minimized if the x value is 3.86 and the y value is, let's say, 4.7, and the minimum value is whatever the value is in here. Sorry, whatever the value is in here. Okay, and but because we are able to draw this function, we know that there is even better solutions in here, etc. But what we have done, without simply without not writing complex code, a simple code, just produce random coordinates. Then evaluate it with the fitness function, and whichever is the minimum, that is the solution. Your algorithm or your program gives a solution within a reasonable time. Maybe this solution is a good one. Of course, you cannot guarantee whether this solution will be a good one, but at least you are able to produce a solution. Is there any problem with this? So the simplest idea is randomly pick points, randomly sample the search space and calculate the fitness values, whichever is the smallest, whichever point produces the smallest f, then feed the user with this value, stating that the function is minimum in here, even though it is not. Do you have any question with this, with that one?
Yok
No.
hocam, kendi adıma.
Tamam, teşekkür ederim. How we will be producing random points? If you remember, I have given you a formula in here, okay? And let me correct this one. A candidate solution will be any value, random value between lower and upper boundary of P, okay? And so what we should do, we should throw a random, we should be calculating a random position on P within the boundaries of lower and upper boundary. And the formula is in here, and I told you we checked it. I gave you the lower boundary value. If 0 comes out, if we throw a random number between 0 and 1, in the worst case, we will get 0, and if random value is 0, we will produce the lower boundary. At most, it will be producing 1. In this case, this formula will produce the upper boundary, and any value between 0 and 1 will produce any value within this area. We already talked about this. Imagine that this function and this problem is two-dimensional. In this case, what we should do on the problem surface, the upper and lower boundary of P parameter, and also we should be calculating the same things, let's say Q, for the Q, and let's say this is the lower boundary and that is the upper boundary of Q. Let me write an example in here. Lower boundary and upper boundary of P, and what I need lower boundary and upper boundary of Q. And let's say lower boundary is 2 and upper boundary is 6. And upper boundary of Q is, let's say, 4. And upper boundary of Q is 5. Okay? And if we would like to randomly create a solution, what we should do, we should produce a random p-value and also a random q-value, because this is two-dimensional. Therefore, what we will do, we will be using that formula for p dimension and also q dimension. Therefore, let's calculate this value in here for p. What is the lower boundary for p? It is 2. 2 plus a random value. Okay, that's a good one. We will need some random values, and imagine that those random values are produced within, I will be giving you some values in here, 10, 8, 75, for example, 40, etc. And knowing that the largest value given in here is 100, if you need a random value, you will simply divide this number to 100, and you will take these random numbers one after another one as necessary. Therefore, P lower boundary for P is 2. We need a random value, and the first number value, random value is 0.1. 10 divided by 100 will give you 0.1 times upper boundary minus lower boundary, which is 4. 6 minus 2, which is 4. 4 times 0.1 is 0.4. Sorry, yes, 0.4. Yanlışım var mı? Yok değil mi arkadaşlar? 4 ile çarpacağız. 4 çarpı 0, 1, 0, 4 verecek. Evet. Benim beynim niye durdu bir saniye? Akşam birdenbire sıkıntıya girdim bir saniye. Lower boundary is 2, and the first P component of the point is 2.4. Okay, and of course, what we need in order to produce this point, we need a Q component. And what is the lower boundary for Q component? It is 4 plus random. We need a random number. The next random number is 0.8. And upper boundary is 5. And lower boundary is 4. Therefore, this is 1. The result is 4.8. Therefore, this is 4.8. Imagine that f function is, as you know, the function of P and Q, and imagine that it is x square minus 4q divided by q, 9q cube plus 4, for example. Imagine that this fpq, this function has a mathematical expression, something like this. What we will need, and what we will need, we have to calculate the fitness value for this point in order to find out where the function f function value is. If you check, what you will do, sorry, I wrote x in here, but actually it is p. Sorry for that. P square, because there is no x in here. P square minus 4 times silgi lazım bana. P square, was it minus or plus? 4 times q, and the bottom is 9 times q cube plus 4. And what we will do, we have to calculate this. 2.4 square minus 4 times 4.8, okay, and divided by 9 times q value. What is q value? 4.8, cube 4.8, plus 4. If you calculate this, you will get what the value is in here. So in order to produce a random solution, a random point, you have to apply this formula to every dimension you have. And every dimension has got its unique upper and lower boundaries. If this problem is 30-dimensional, so you need 30 lower and upper boundary pairs in order to define your search space. And also for each dimension, you will be using this formula and you will be applying this random operation, and those random values will be taken from here, and then you will calculate the point, then feed it into your fitness function and get the fitness value. If it is small enough, or if it is the smallest than what you tried, how can I say, what you have found so far, that will be your minimum point that you have found during your research, during your search. Anyway, let's come back here. Where was it? In Langerman. Imagine that after talking about this, the best thing is, if you remember, I told you that what we can do, we can randomly sample the search space and hope that we will find where the minimum is. But more, how can I say, disciplined way to search rather than randomly sampling the search space. The more disciplined way is to make a grid search. Do you know what grid search is? Grid search. Have you ever heard about it?
Yani şöyle tahmin ediyorum. Bu, mesela ayırdığı 0, 2, 4, 6 diye ayırdığı küçük kareleri mi arıyor sırayla?
No. What we are doing is we will define a step size. Okay. Let's say step X and step Y. Okay. And we will do, in 2 for loops by within the lower and upper boundaries. With the we will be increasing x values with the step size, and let's say step size is at the beginning is 2. Let's say step x is 2. It means x will get the values 0, 2, 4, 6, 8, and 10 when y was 0. Then we will increase y value by step y. Um, uh, then the coordinates will be, the samples will be those. These marks that I have marked, and then we will increase y value once more. Then we will sample those places. In the end, those points and the search space will be equally spaced. Equally spaced. It will be sampled by the distances that are where the distances are equal to each other. Anlatamadığım gibi hissettim. Yani 2 tane for döngüsünün içerisinde y'yi step size kadar arttırıyorsun. X'i de step size kadar arttırıyorsun ve dolayısıyla eşit aralıklı noktalar buluyorsun. Yani sample'ını eşit aralıklarla yapıyorsun. This is called grid search. Rather than taking the samples randomly, what you are doing, you are not missing out any part of the search space. Every area in the search space has the equal chance to be explored. But as you can guess, if the step size is too high, that we will be missing some important parts. But if we take it smaller, then we will be sampling, we will be taking more samples. Those samples will be equally spaced, and but in this time the number of samples will be enormously increased, then quadratically increased for two-dimensional search space, and that will be taking a lot of time. And the smaller the step x is, the smaller the step sizes are, the better the higher the chance of finding the actual or global optimum point. But this will cost us a lot of time, a lot of computation. In order to how can I say, this is not feasible. Of course, by selecting as small, reasonable step size, you can reasonably sample search space. But if it is too large, you may miss out. Or if it is too narrow, if it is too small, the step size is too small, then the number of samples will be increased, and this will cause trouble because of the time it takes. But instead, what we can do, we can use a large space, large step size at the beginning. Let's say step size is 2. In this case, there are 1, 2, 3, 4, 5, 6, 6 points in one dimensional. 1, 2, 3, 4, 5, 6, 6, 6 sampling points in another direction. Therefore, there are a total 36 samples if we take step size 2 within the upper boundary and lower boundary, which is 0 and 10. We already described it, or we already given in here. So with the help of 36 samples, we will have an rough idea, course idea, course. How can I write course? Course. That is A arkadaşlar. Course. Course. Okay. We will be coarsely taking the samples. Of course, these samples are equally spaced, and we will have an idea where the function is minimum. After that, after taking those 36 samples, we will find where the whichever sample is the minimum. Let's say this sample is the minimum. Then what we will do, we will narrow down our search space around this point, and we will be ignoring the remaining parts, and whichever point, whichever sample within those 36 samples is the minimum, we will be taking it to the central, and we will put our search space around this point. In this case, the new upper and lower boundaries of y and lower boundary and upper boundary of x will be changed, and let's say upper boundary and lower boundary is 0, and I'm talking about for x, and 4, upper boundary is 4, and for y it is, let's say, lower boundary of y is 1 and upper boundary is sorry, not 3, 5. Okay, so rather than searching the whole space, we will be searching a narrower area, and we will be sampling, uniformly sampling with a new step size. At the beginning, the step size was 2, and that gave us 36 samples. Now I will be reducing it to 1. Step size is 1 now. Therefore, there will be 5 points between 0 and 1, and the step size is 1, and there are 5 points between, sorry, 5 points between 1 and 5. Therefore, we will be taking 25 samples within this area, okay? And that will By this way, we will have more chance to find global minima. After that, we will identify whichever sample has the smallest value. Let's say that one, and then we will be centering. Let me put this one, and even a narrower search space will be around the lowest sample that around the sample that produces lowest fitness value. Let's say this time the lower boundary is 1 and upper boundary is 3, and the step size will be taken, let's say 0.1, and therefore we will be sampling 20 points in here and 20 sampling points in other dimension, and we will take 400 samples, and we will most probably catch this value. As you can see, what we have done at the beginning, step size was large, then we reduced it, then in the third step we reduced it even further, and this will give us in the meantime, rather we didn't use the original upper and lower boundaries. Each time we decreased the step size, we also decreased upper boundary and lower boundary, let's say 50% in every direction. And if we do so, we will be taking more samples around the possible optimum point, and eventually we will get where the minimum point is. This kind of search is called course to find. Course. Text yazabiliyorum değil mi ya buraya? Yazabilme şansım var mı? Yok. Çıkayım şuradan. Nerede yazabilirim?
Şeyde girişte tekst eklenebilir hocam galiba ama slaytı bu sefer şey yapmamız gerekecek.
Şöyle yapayım. Hemen alayım şuraya yazayım ya. Course to find arkadaşlar. Course to find search. Okay. Rather than uniform search, what we were doing with uniform, we were taking samples uniformly spaced, and whichever result is the minimum, it is we are claiming that it is where the optimum point is. But this will, as I told you, if we take let me bu sefer de farklı burada. Okay. Imagine that we are taking the step size are large, then in every direction, of course, we will be applying this. The crossing points will be our sample points, and then we will feed this to fitness function, and we will get the result. And this kind of search is called grid search. But with the grid search, the sample size, the step size is very important. If you take it smaller, we will get more samples. That means we will have more chance to find the optimum point. But this time, of course, I don't want to draw the rest. And each crossing point will be a sample, and the number of samples will be increased quadratically for two-dimensional problems, and this will take a lot of time to calculate. And this is still a grid search, okay? And as you can see, if we take the step size smaller, we will have higher chance to find, but it will take a lot of time. And in order to avoid this problem, what we are applying, we are using course to find approach. At the beginning, the step size are large, so we are having a large grid on the search space. Then by decreasing, finding where the minimum is, of course, where the minimum sample point is. After that, we are putting another grid around in a reduced search space around this minimum point, and exploring even more, creating new solutions, new samples around this minimum, and hoping that the global minimum is somewhere around. Okay. Kaydetmiyorum, çıkıyorum. Let's carry on. Okay, I mentioned about grid search, I mentioned about course to find, and also I mentioned about this formula is necessary to calculate a point for each dimension, of course. If the problem is 20 dimensions, so what you have to do, you have to find 20 component of that point, and also you will need random values, and those random values will be given to you later on. Anyway, so now I'm talking about hill climbing algorithm, arkadaşlar. Hill climbing algorithm is the simplest algorithm, maybe, in order to find out the global minimum. What we will do, first of all, for one-dimensional problem I'm talking, first of all, we will produce a candidate solution by using this formula. Then, within the neighborhood of this solution, which is given here, we will create a random solution. I'm talking about hill climbing algorithm now. So produce a candidate solution, then within the neighborhood of this solution, produce another solution. Let's say this one. If this solution is better than the current one, then we will be accepting this solution, and the current solution will be here. Okay? And we will be accepting this solution, and we will say that the new solution is here. Then what we will do, within the neighborhood of this new solution, we will create a random solution, and if it is a good one, for example, like this, we will accept that one, and we will move towards where the global minimum is. Of course, we created a random solution. And now I'm talking about another case. We created a random solution, and within the neighborhood of this solution, we created another solution. But this time, the solution is not good. The current solution is better than the candidate solution, which is, we tested it and it is not good, and we will reject this one. So we will be only accepting good solutions, but we will be rejecting bad solutions. If we reject bad solution, the current solution will be still our solution, and if we accept the solution, then our current solution will be this accepted new solution. It will be the accepted new solution. Okay, so we already talked about this anyway. By using this idea, imagine that we are here, and currently we are here, and we have another, we are testing whether we should be accepting this solution. When we checked if this is a minimization problem, let's say this is current or old or current, let's say current. and this one is next. Okay. What we are doing, we are checking the fitness function of current and fitness function of next. If the solution we are testing is better than or equal to current solution, we are accepting it because it is a better solution. Otherwise, reject. Otherwise, reject. Buraya teksti de yazabiliyor olmamız lazım yani. Neyse. Anyway. So, if we accept that solution, it means in the next iteration, we will do the same. Within the neighborhood of this current solution, we will create another random solution. Let's say we created this solution, and when we checked, it is no good. Therefore, we will reject this solution and we will stay where we are now. And if we find then in the loop, we will create a random solution within the neighborhood of the current solution. And then if we find a better solution, we will accept it and we will move. And as you can guess, this will take us to the where the local minima, or if we were here, where the global minima is. But by luck, if we are here, we will never get out of this place because that is the best place. Whichever solution we produce within the neighborhood of this solution, it will be always worse than the current solution. Therefore, we will keep rejecting it. So the algorithm will get stuck into a local minima, and we will not be able to search the remaining parts. Is that clear? Hill climbing is very simple. Produce a solution, call it current solution, and evaluate it, and create another solution within the neighborhood of current solution. And if it is better, then accept this solution as current solution and repeat the process once again. Otherwise, but when I say otherwise, if the candidate solution is not a good one, then reject it. Current solution will be still current solution, and we will be looping again. We will be repeating the whole cycle again. Within the neighborhood, create another solution and a candidate solution, whether accept or reject it, and this will be going on until there is no acceptable solution is, and in this case we will be trapped in either a local minima or a global minima. Do you have any question with the hill climbing algorithm?
Yok hocam.
It is very simple. It is very stupid, if you ask me, but it is working. You can program games, intelligent games, only applying such a simple strategy. Who is talking now? Selin, sen mi konuşuyorsun bu arada?
Evet hocam.
Okay, let me ask you, how can you improve this algorithm? Do you have any
Yani
suggestions?
şöyle, ilk yani bulduğumuz bir sonraki kötü çözümü kabul etmediğimiz için sürekli lokal kısımlarda takılıyorsak, kesin bir çözüm olmaz belki, çok aşırı ilerletmez ama mesela, bir önceki çözümü de kaydeden bir sistem yapıp birkaç tane kötü çözümü tolere edip daha sonra bakıp belki daha iyiye giden bir şey olabilir. Mesela bu örnekte, lokal minimadan sonra hemen yukarı çıkıyor ama daha sonra da hemen global minimaya inen bir tane, yokuş aşağı var.
Hı hı.
Yani birkaç sample daha kötü hani olabilir deyip kabul etsek daha geliştirmiş olabiliriz bence.
Kötüyü de kabul edersek, sanki bu iş olacakmış gibi görünüyor, öyle değil mi?
Hı hı. Yani şu ana kadar bulduğumuz en iyi çözümü gene kaydedelim Ama birkaç tane kötüyü daha tolere edip belki, kısa süreli bir yokuş yukarı vardır. Daha sonra tekrar aşağı iniyordur, onu kontrol edebiliriz.
Okay. This idea is applied in simulated annealing. I will be introducing you shortly, okay? Very much like, I mean, because what you are telling us, rather than rejecting the best solutions, sometimes accepting them could be could yield a better solution. I mean, it may help us to climb up such hills and then find out where global minima. It may help us to find the global minima rather than getting trapped into local minima. So we shouldn't be so rigid to reject bad solutions, and simulated annealing is making this, it is gevşetmenin İngilizcesi neydi? Loosening this rigid rule by the favor of bad solutions, accepting bad solutions. But in the daytimes, with the daytime students, what I suggested to them, I said, how about changing the neighborhood size? I mean, if you go back, the neighborhood dimension, where was it? Okay. Plus minus the neighborhood radius, if you remember. If we increase the neighborhood, if we make it wider, then the random value we will be producing may get a chance to roll down to where the global minima is. Okay, so rather than keeping the radius, neighborhood radius, constant, we may make it variable. So this may be another solution for not being trapped in local minima. Selin, is that clear?
Anlaşıldı hocam, sıkıntı yok.
Do you think that it may help?
Yani edebilir.
Do you remember Levy flies I talked about earlier in last week?
Ha, şu, exploration ve, exploitation içinde olanlar değil mi?
Okay, yes. And now imagine that we have a function, something like this, 0, 5, and 100, let's say. A linear function between 1 and 0.1, and another linear piecewise function between 5 and 100. So I have drawn a piecewise linear function in here. Between 0 and 5, it has a steep slope. Okay, it is decreasing from 1 to 0.1 with that axis is changing only 5 units, and the vertical axis is dropping from 1 to 0.1. But after that, 45 units, it is decreasing only 0.1. So what I will ask you, give me some numbers random numbers between 0 and 100. Could you please tell me?
67.
67. Carry on. Söyle. Bol
Eee,
bol ver.
normal sayılar. 57,
57,
12,
12,
83,
83. Okay.
10,
10,
27,
27,
2.
2, belki 90. Değil mi?
Hı hı.
Okay. Now, what you have done, imagine that we have a function for d, but this time the function d is, the neighborhood radius is not a constant, but it is the function of r. Okay, r is given in here. Okay, and what it is, imagine that this is, give me a name for that. Let's say m. M is the function of r. Okay, and mr times d max. We say that d max is 100. We set d max, maximum radius, as 100 units. Okay. So for this sample, throw a random number, which is 67, and come up here and find out what MR value is for 67. And you will see that it is a very small number. I'm not capable of calculating it now, but imagine that it is 0.5, let's say, okay? Is there any problem with this value, 0.5? It could
Yok hocam.
be. It could be 0.5. So the radius for the neighborhood will be 0.5 times d max, which is 100. Therefore, we will set the neighborhood as 5, because 0.5 times 100 will be 5. Therefore, the candidate solution will be within this neighborhood. And let's say we've checked this one and we rejected it. And now we are in here. The next solution will be produced within the neighborhood. What is the radius? It will be calculated from here once again. And the next time we will take 57 and we will feed it into MR, and it will give us something very near to 0.05, let's say 0.049. And it will be more or less that large. Okay, all these values, 12 will be even larger. If it is 12, it will be somewhere here, and it will be like 0.8. 0.8 will give us 8. The radius will be 8 units. It was 5 units, now it will be 8 units. We are not, what are we doing? We are using a dynamic neighborhood radius. Okay, but time to time, you will get values like 2, which is less than 5. If it is 2, then it will be how much? It will be something like 0.6. If it is 0.6, 0.6 times 100 will give us 60, right? 60 D max will be, rather than being 5 or 6, it will be 60. So time to time, we will be jumping to another location. And then while we were here, then once again, we will randomly calculate radius, and more likely it will be small. So we will be exploring this area. Then all of a sudden we will get a large neighborhood, and this will give us to jump somewhere else. So if you remember Levy flights, it was something like this. It was coming and exploiting a region, then all of a sudden jumping another direction, then doing an exploitation, then exploring another part, and it was something like this. This function is very much like Levy function, and it is giving us when we will be jumping. And as you can see, if you produce 100 numbers with a random number between 0 and 100, 95% of the numbers will be larger than 5. And only 5% of them will be smaller than 5. If it is smaller than 5, the jumps will be larger because the coefficient, MR coefficient will be high. Therefore, a sudden large jumps will be occurring. Otherwise, the step size will be, the neighborhood radius will be smaller, and then we will be, exploring where the current solution is. I mean, we will be exploiting, sorry. We will be exploiting where the current solution is, and time to time, if a small number comes up, then it will be jumping another section of the search space, and by this way we will be hoping that we will be freeing, we will be getting loose from that trap, okay, and we will be exploring the search space. Anlaşıldı mı?
Anlaşıldı hocam. Yani şöyle, aslında sayıları rastgele seçerek, yani yeni bölgeler bulma ve bulduğumuz bölgeyi arama arasındaki dengeyi kurmuş oluyoruz. Çünkü uç değerler zaten sürekli gelmediği için o denge de sağlanmış oluyor.
Evet, oradaki 5'i mesela atıyorum 10 yaparsın. %10 ihtimalle uzağa gidebilme şansı veriyorsun. Gidecek diye bir şart yok ama gidebilme şansı veriyorsun. Öyle değil mi? Yani attığın sayı belki de hemen yanı başında bir değer de üretebilecek. Hani komşulukta üreteceksin ya. Bu komşuluğun neresi olduğunu söylemek için kullanıyorsun bunu. Daha sonra bu komşuluğun içerisinde çözüm buluyorsun ya. Yani şu artı eksi D vardı ya burada. Normalde şu maviyle gösterdiğimiz yerdi ya. Şurası mevcut çözüm burasıysa buna artı D eklediğim zaman yer burasıydı. Eksi D eklediğim zaman yer burasıydı. Dolayısıyla bu neighborhood radius'u ne yaptım? Random sayının fonksiyonu haline getirdim. Random sayıyı nereden hesaplıyorum? MR'dan hesaplıyorum. Gelip buradan hesaplıyorum. Random bir sayı atıyor. Buradan bir katsayı alıyorum. Bu katsayıyla da radius'unu belirliyorum. Diyorum ki radius'um atıyorum şurası olsun. Şöyle oluyor. Dolayısıyla bu bölgede herhangi bir yere atla dediğim zaman şu an buradayım. Bu bölgede herhangi bir yere zıpla dediğimde random bir sayı üretmen gerekiyor. Geldin mesela şurayı üretebilirsin. İlla ki uzağa üretecek diye bir şart yok. Ama gidebilme şansı vermiş oluyorsun. Anlaşıldı mı?
Anlaşıldı hocam, sıkıntı yok.
Okay. Senin üzerinden diğer arkadaşlarım da eğer varsa sıkıntıları lütfen söylesinler. Yani biz seninle konuşuyoruz şu an. Bu benim için daha iyi oluyor. Ama varsa arkadaşım, herhangi bir sıkıntı çeken arkadaşım bahsetsin lütfen.
Yok
Okay.
hocam, dinliyoruz.
Sorun yok. Teşekkürler Şemsettin. Bu sesi tanıdım sanki. Ee, devam ettik, devam ettik. Hill climbing'den bahsettik. Dedik ki burada lokal minimaya sıkışmak bir problem. Bunu çözmek için ben radius'u yani komşuluk radius'unu dinamik hale getirerek çözmek istedim. Ama Selin arkadaşımız da dedi ki ya accept ederken ya pardon reject ederken bu kadar katı olmasak dedi. Şimdi simulated annealing'i anlatacağız ve Selin'in istediği gibi bir şey gerçekleşecek. The next algorithm is simulated annealing. Simulating annealing is a process of melting down the metals and making metal atoms float in the making the metal in liquid form, and the atoms will be swimming all around and freely with an energy level. And then if we cool it down, then those atoms will be bonding together in a crystal, if it is capable of producing crystal structure, they will be bonding crystal structure, and it will make the metal more resistible, as in the case of steel. If we heat up the iron, by hammering down or with the help of oven, we will be heating the iron in very high degrees, and then the atoms will be almost floating in the metal. It will not be in liquid form, but it will be almost, the atoms will be will have a high energy level, and it will be floating inside the surface. And then if we put this iron, hot iron into water, we will be cooling it down, and then making the iron bond with other iron atoms in a crystal manner, and then this will create a steel which is stronger than iron. So that is annealing procedure, and by the help of, I mean, the idea is coming from that annealing procedure. And what we will do, as Selin suggested, rather than rejecting a bad solution, we will be accepting that each solution has an energy level, okay? And at the beginning, we will be introducing a heat or temperature in the search space, okay? At the beginning, the temperature will be quite high, and those atoms, the solutions will be called as atoms with the energy levels. Those energy levels are the fitness values of these atoms, these solutions. And we will accept that at the beginning, the temperature is quite high, and therefore the temperature, the atoms are moving freely. Moving freely means accepting the bad solutions, accepting the candidate solutions, even they are worse than the current solution. The hill climbing was definitely rejecting bad solutions, but the simulated annealing, in the simulated annealing algorithm, if the temperature is quite high, then the bad solutions will be accepted. And if the temperature is low, the algorithm will become very much like hill climbing, which it will be rejecting the solutions. So a new concept, temperature, will be introduced to the solution space. So at the beginning, in the loop, if you remember, in hill climbing, the search process was in a loop, and every time in each loop, we will producing a candidate solution, and we will be rejecting or accepting it. And of course, at the beginning of the iterations, we will introduce a temperature to the solution space, and we will accept that the temperature is high. With the as the iterations advances, then the temperature will be cooling down, and we will say that the temperatures is quite low now. Nasıl yaptım bunu bilmiyorum. Okay. So let me show you. With simulated annealing, we will be introducing a temperature with the iterations, and at the beginning, iteration is maximum. Then with each iteration, it will be cooling down, and we will use a formula to cool it down. In linear cooling procedure, it is the formulation is given like this, and maybe we will be cooling down the solution space with exponentially by using this formula, or even we will be cooling it fast, then it will be cool. It will keep cool in most of the iterations, and this one will be called be fast, and the formulation is given here. And maybe we will prefer to cool it down fast, then we will not let it go to 0, but it will remain it will be converging to a value which is called Boltzmann value, and the formula is given like this. So cooling is an important concept of annealing process. So in simulated annealing, we will need a temperature value, and that temperature value is usually, not usually, always quite high at the beginning. As you can see, it is always high. Then it is going down, it is cooling down, sometimes linearly, sometimes exponentially, usually exponentially. And by this way, at the beginning, we will accept the worst, even the solutions are worse than current solution, and we will say that the atoms are freely moving at the beginning. Then we will not let bad solutions to be accepted with the higher iterations. Okay, so Selin's idea will be integrated with the help of temperature value. And also, let me show you how we will do this. Where is that? Okay. Let me show you what e minus e power minus x function. That is x, and that is fx. This is fx, okay? This is fx. If x is 0, e power 0 will be 1. And it will be decreasing exponentially. When x goes to infinite, it will be 1 e power infinite, because it is minus, as you can see. 1 divided by infinite is 0. Sorry. Sorry. E power infinite is infinite. 1, if we divide 1 to infinite, it will be 0. So it will be decreasing exponentially, then it will go to 0 with the as the x gets larger. This is a power minus x function. Now we have got a value called p acceptance, and I will talk about this later on. Actually, let me talk first. Where was it? Now, imagine that we are currently here. Okay? If I'm talking about simulated annealing now. We are currently here. And within the neighborhood, we created a solution which is better than the current solution. We will definitely accept this solution, and this will be current solution. Then the first iteration is finished. Next, within the neighborhood of this current solution, create a random solution. Imagine that we created this one, worse than the current solution. Then we will check, we will decide whether we should accept this one or not. In order to do that, we will introduce a random threshold value, which is called p acceptance. Okay, p acceptance. And we will throw a random number. If the random number is smaller than acceptance threshold, we will accept it even though it is bad. even though it is not a good solution. Time to time, we will be accepting bad solutions, and how we will decide this? But with the help of this threshold value. This threshold value is not constant. For example, if I say that 0.5 is my threshold value, then throw a random number. 50% of the numbers will be less than 0.5. So half of the times we will be accepting bad solutions. Otherwise, we will be rejecting it. And that is a constant constant acceptance ratio. Okay, acceptance, probably acceptance threshold value. Let's say if it is 0.9, 90% of the times we will be accepting bad solutions. If it is 0.1, 10% of the solutions, bad solutions will be accepted when they were worse than the current solution. Is that clear? So what we will introduce? We will introduce a threshold value, whether accept a bad one. But rather than using a constant value, with simulated annealing, we have a function for it in order to calculate the acceptance threshold, which is, it is given as E power minus delta over K T. As I told you, T is the temperature. So acceptance ratio, acceptance threshold is the function of temperature. And also it depends on delta, and K is a constant number. So let's not talk about it for the time being. Now, in order to accept or reject a bad solution, we should throw a random number. If we should throw a random number, if it is smaller than, and also equal than, let's put equal. If it is smaller than acceptance threshold value, which is given, the formula is given here, then we will be accepting this solution. Otherwise, we will be rejecting it. And the acceptance threshold is given with this formula, and it depends on delta and T. T is temperature. Delta is defined as E new minus E old. Actually, that is called energy level of new solution, energy level of old solution. That old means the current. New solution is the solution that is produced within the neighborhood of current solution. Okay, this is the candidate solution's fitness value. Fitness value. This is the fitness value of current solution. Therefore, this is F current, and that one is F candidate. F candidate means fitness value, even though we call it energy because it's simulated and in simulated annealing. In annealing procedures, we are talking about energy level of atoms. Therefore, to make similarity, we call it energy level. Actually, we are talking about fitness value. Anyway, do you have any question up until now?
Yok hocam.
Okay. So, knowing this function, let's talk about how temperature and how delta is affecting the problem. And please don't forget that this formula is valid for minimization problem. Okay, if we are talking about minimization problem, we should be using this formula. If it is maximization, the formulation should be modified. Anyway, now let's talk about the effect of temperature on the acceptance threshold. Imagine that we have a current position which is producing F current and a candidate solution producing F candidate. And this difference is occurred in different times of temperature. Okay, what I mean is if this difference, let's say delta has a value, whatever the value is, whether we will be accepting this solution while it is cold or very hot. Okay, we will be discussing this. So let's keep delta as constant, K is constant, and therefore the formula is something like E constant T. Okay, delta K, what we have done, we accepted this as constant value C. So E power minus constant T. Now let's talk about this formula. I'm keeping, I'm ignoring actually, I'm ignoring delta value. I just want to observe how the algorithm will be treating a solution, the same situation in high degrees and low degrees, okay? So imagine that temperature is quite high at the beginning. So a number divided by a very hot, which is infinite, let's say. So let me write this one as 1 divided by a power t. Okay, this is equivalent to this one. If the temperature is infinite, what will be the value of this function? If t is infinite, number divided by infinite will be 0. E power 0 will be 1. 1 divided 1 will be 1. So acceptance ratio will be 1. Acceptance threshold will be 1. So when you throw a random number between 0 and 1, it will be less than 1. So we will be accepting any solution, any bad solution. Is that right?
Öyle olması gerek.
Okay, so no problem with that. How about if the temperature is very low, almost 0? C divided by 0 means infinite. E power infinite is infinite. 1 divided infinite is 0. Therefore, acceptance threshold becomes 0. So if you throw any number between 0 and 1, it means almost all of the bad solutions will be rejected because acceptance threshold is 0. Unless the random number is 0, we will not be accepting solutions. Is that clear? So the temperature is affecting the same situation for, I mean, we are not considering whether, I mean, how can I say, if the difference between two solutions are, the current solution is, sorry, the new solution is worse than the current solution. Let's say the difference between them is 7, let's say. And we don't want to accept this. But if the temperature is high, we will be accepting this solution while delta is 7. The same difference which is 7, will be accepted if the rejected if the temperature is quite low. Therefore, the acceptance ratio is acceptance threshold, not ratio. Acceptance threshold is temperature dependent, and temperature depends on the iteration, and therefore at the beginning of the iterations we will be exploring the search space by accepting the bad solutions. Later on we will be accepting only good solutions. It means we are exploitation the search space. Okay, this is the effect of temperature. Do you have any question with that?
Yok hocam.
No. How about delta, the effect of delta? Let's see. Now, this time, let's keep temperatures constant. Let's say temperature is quite high or normal or very high. It doesn't matter, but it is in one condition. And how about the delta? Let me show delta like this. And in this case, we are keeping KT as C, keeping constant, okay? And depending on the delta, we will be analyzing the acceptance probability. If the difference between new and old is very small, let me write this one once again. It is something like this, right? Now, if delta is very small, very small, almost zero, in this case, it will be 0 divided by a constant number will be 0. E power 0 will be 1. 1 divided by 1 is 1. Therefore, acceptance threshold will be 1. Therefore, regardless of temperature, if the new solution is almost as good as old one, the current one, the difference is very small, then acceptance of this bad solution is almost certain. We will be accepting it. Whichever random value we throw between 0 and 1 will be less than acceptance threshold, then it will be accepted. So the acceptance is not only determined by temperature, but also the goodness of or badness of the new solution's fitness value. Therefore, if we keep T constant, if the solution is the delta is 0, almost 0 or near 0, the acceptance rate will be quite high. The bad solutions will be accepted, regardless of whether we are in the beginning of the iterations or at the end of iterations. It doesn't make any difference. Also, if the delta is quite high, very high, let's say the difference between current solution and the new solution is infinite. In this case, e power infinite will be infinite. 1 divided by infinite will be 0. So acceptance threshold will be 0. So even though at the beginning temperature is quite high, we will not be accepting if the solution is quite bad. Okay, we want to accept bad solutions, but we don't want to accept very bad solutions. As you can see, the acceptance threshold is governed by delta, the fitness of goodness of the new solution, and also the temperature. So as you can see, it is not as straightforward. It's not as constant acceptance ratio threshold, but it is the function of two variables, delta and temperature. Okay, Do you have anything to say?
Anlaşıldı hocam. Sıkıntı yok.
Okay. Dolayısıyla istediğin gerçekleşti mi? Kötüleri bazen de
İstediğim oldu.
İstediğin oldu. Hatta istediğinden daha da güzel oldu.
Evet.
Ve dolayısıyla simülatif annealing'i icatlamış olmuş oldun. Bir nevi aslında şey yapmış oldun. Önerisi kafayı biraz yorsaydın bu algoritmayı çıkartırdın sen eminim.
Bu
O
biraz
halde
daha dinamik bir şey oldu.
ama şu, benim dersimde, hep söylerim size, yani yapay zeka dersinde asıl vermeye çalıştığım şey düşünceyi, yani bu düşünce niye var? Bakın, Levi Flight dedik, oradan bir düşünce aldık. Mesela Levi Flight'ı bunun içerisine entegre edebilir misin?
Yani nasıl yapabiliriz onu? Eee, Gene aynı şekilde soğuma, ısınma sistemini tutarız. Ama, bundan bir önceki gördüğümüz gibi, şeyleri, noktaları gene rastgele belirleyip o şekilde belki yapabiliriz.
Yo, yo, hani az önce, Levi Flight'ın formülünü vermiştik, hani random sayılar atıyor. Simulated annealing'de bizim kontrol ettiğimiz şey sadece temperature ve delta değerine bakarak yapıyoruz ya. Ve unutma, yeni çözümü nerede üretiyoruz? Komşuluğumuzda üretiyoruz. Komşuluğa dokunuyor muyuz? Hayır. Komşuluk hep sabit simulated annealing'de. O zaman komşuluğu da, Levy Flight'la yapacak olursam, yani, Levy function'dan geçirerek dinamik bir random'a bağlı bir, zaman zaman büyüyen, zaman zaman küçülen hale getirecek olursam, sıkışmanın önüne geçmiş olurum. Yani komşuluk çapını doğrudan getirip oraya bağlayabilirim sabit kullanmak yerine. Ya da
Anladım hocam, evet.
ya da birkaç iterasyon boyunca çalıştırdık, bir türlü improve etmiyor solution'umuz. Improve etmeyince o zaman hemen dinamik bir şekilde de, şeyi değiştirmeye çalışabiliriz, komşuluk çapını. Büyük bir şeye çekip sonra tekrar, düşüğe çekebiliriz. Böylece bulunduğu lokalden, sıçramasını sağlamış olabiliriz. Anyway, this is the pseudocode of simulated annealing, and it is not fully correct. Let me see. At the beginning, by the way, create a random initial solution. I don't know the letter. Is it eta? I don't know. It is a Greek alphabet. Let's say initial solution is C, and what we will do, actually, we need that value. Okay, all the time we are looking for what the solution is, and the solution is given with this Greek letter, and that solution's cost will be assigned as the energy level. Actually, this is the fitness cost is fitness function. So we will create a random solution. Then we will calculate the cost, and we will be assigning it to uh, current solution. Current solution's fitness value. Then what we will do, we will be in a loop we will start temperature from temperature max to the minimum value, temperature minimum, with a function of temperature. It could be a linear cooling procedure, it could be fast cooling procedure, depending on the cooling function you are using. So it will be decreased with the help of function in here. Then we will create a new solution within the neighborhood of current solution. Current solution is will be called old, and candidate solution will be new. Okay, new solution, and we will calculate the cost of this new solution, and we will assign it to energy new, and calculate the delta. Now, if delta is smaller than 0, it means we have to talk about this. Now, if this is, don't forget that this is a minimization problem. Okay. And if it's a minimization problem, if E old is 4 and the current solution is 4 and the new solution is 3. Is it a good one? Yes. So we should accept this. So 3 minus 4 will be minus 1. Therefore, if delta is, it says delta is larger than 0, it means the else part will be working. So the new solution will be accepted and it will be assigned to as our current solution. Of course, it is assigning the fitness values, but in the meantime, we should be keeping the positions as well. So it is missing in here. So if the solution, new solution is better than the old solution, we will be accepting it. If it is worse than the current solution, in hill climbing, we were rejecting it, but in simulated annealing, we are checking whether we should accept or reject it. So we calculate P acceptance acceptance threshold, and throwing a random number. If it is, let's correct this one. If it is less than or equal to that random number, we will be okay. Okay. Arkadaşlarımıza birinci öğretimde de söyleyeyim. Burayı düzelttik ama iyi okumadan düzeltmişiz. So bir hata yokmuş. Özür dilerim arkadaşlar. If the random number is larger than the threshold value, we will be rejecting it. Reject. Otherwise, we will be accepting it. So while talking in here, we were accepting it if it is smaller than the value, the threshold value. In here, we are doing the opposite way, but doing the same thing, but in another way. So if we keep this like this, we will be accepting it. Otherwise, we will be rejecting it. So there is no mistake in here, okay? So the slide doesn't need to be changed. Everything is working properly, but please don't forget that you have to keep where the current solution, and when you transfer, when you accept it, also you have to record where the this good solution is found, and always carry out with throughout the program. Do you have any question?
Yok hocam.
Ya son kısımda biraz kargaşa oldu çünkü şuradaki ters mantığı şeye kaçırmışım ben. Yani şöyleyken, yani büyükken, threshold value büyükken kabul etmemiz gerekiyordu. Zaten aynı şeyi söylüyor. Eğer random sayı büyükse rejected, değilse kabul etmiyor. Ben anlatırken ters şekilde anlatıyorum ama aynı şeyi anlatıyormuşuz sonuçta. Dolayısıyla bir hatamız yokmuş. Okay. O tartıştığımız çok soğuk olma, çok sıcak olma davaları burada var arkadaşlar. Anything else? Okay. If the cost function is not smooth, okay, the simulated annealing algorithm will not be functioning properly. If it has abrupt changes like this, as you can see, it is quite smooth in here, but all of a sudden it goes, I mean, it has got a minimum point in here. So this it will be deceiving for the algorithm, and in order to find out minimum, it will be following that path, but all of a sudden there's a sudden changes here. So simulated annealing will be failing to find where the minimum is. But for example, in this one, most probably it will be finding the minimum point because there is no sudden abrupt changes in the cost function. So if you can write a smooth cost function, you should be preferring that smooth function. The function, your fitness function, shouldn't have sudden changes in the search space. We already talked about cooling procedure. Okay. I don't want to repeat myself. And one last thing, re-annealing procedure. Okay, what is re-annealing? Imagine that we have 1,000 iterations. We determined that we will be running simulated algorithm with a loop which has 1,000 iterations. But if we are using a linear cooling procedure for this 1,000, what will be the cooling procedure? It will be like this. Okay, so running simulated annealing with Emax 1,000. The cooling procedure will be that line I'm drawing if we are using linear cooling procedure. But as you can see, what we will be doing, we will be running the algorithm once. However, keeping the maximum iteration as 250 and rather than running it in a long time, if we make it smaller, heat it up, then cool it down. Then later on, once again, heat it up, then cool it again. It means re-anneal. And then do this 4 times. It means you are as if you are running the algorithm 4 times within the given number of maximum iterations. So applying re-annealing may help us to free from the local traps. So imagine that in the let me show it in here. That is the cooling procedure. Imagine that we heat it up, and then when we when we cool it down, the algorithm get trapped in here. So when we heat it up again and cool it down, during that heating up, it may climb up and it may reach here, and then it will go and find the global minimum. Therefore, rather than running once, it may be, and in a long time, of course, 1,000 iterations, it may be a good idea running it in short cycles, like 250, and then heat up again, then cool it down, heat up again and cool it down, and do this 4 times, maybe 5 times, depending on your choice of maximum iterations. And by this way, if you get trapped into a local minima, you will be, you will be freed up, and you may find where the global solution is. So I have introduced you with re-annealing procedure. Do you have any question? Because the class is finished now. Sorunuz varsa alabilirim arkadaşlar. Herhangi bir yeriyle ilgili bugünkü anlattıklarımızın.
Yine kendi adıma benim anlamadığım bir yer yok hocam. Teşekkür ederiz.
Evet. Bu re-annealing kavramı bir kere daha karşımıza ileride defalarca, hatta her algoritmada bir şekilde kullanacağız. Çünkü bir defa çalıştırmak yerine birden fazla çalıştırmanın yararını görüyoruz. Dolayısıyla genetik algoritmada deneyeceğiz bunu başka bir şekilde. Karıncalarda deneyeceğiz başka şekilde vesaire. Şemsettin, sanki sesini duyduğum gibi bir şey söyleyecektin.
Yok hocam, şu an bir şey yok. Kayıttan
Yok.
sonra.
Kayıttan sonra pekala. Başka bir şey yoksa kaydı durduruyorum. Ondan sonra kaydı durduralım önce.